So hello everyone, this is lecture 37 for the classical physics. In the last lecture we have completed this thing, means we have found the normal frequencies, we have found the normal modes, and I already defined you what is the meaning of normal modes, what is the meaning of normal frequency. So normal frequencies are those frequencies at which these all particles will be oscillating. So this equation we find it, where this omega 1, omega 2, this matrix will be solved and it will give you us multiple values. So that will be our normal frequencies, and corresponding to them we will get a eta 1, eta 2. So eta I will give you your normal modes. So I told you what is the meaning of mode. So it is eta I will be eta I, eta 2, eta 3. Then these values will represent you or tell you that how the particle or the mass is oscillating. So just like I gave you the example 1 minus 1. So 1 and 1 means first and third are moving in same direction, and minus 1 is in opposite. So this is representing the displacement. So it is minus displacement means it is going in this direction, and positive displacement means they are going in this direction. So that's how we find the direction. Now today let's see what are non-degenerate frequencies. Now we will get multiple frequencies here. So maybe we will get some two frequencies same, just like we will get omega 1, omega 1 in place of 3, means 3 and 1 are same and omega 2 is different. So if all the frequencies are different, then we call them non-degenerate frequencies. Okay, means no two are same, then we will call them non-degenerate. If all the normal frequencies are different from each other, then we call them non-degenerate frequency. Omega I should not be equal to omega j. But if any of 2 or 3 are same, then we call them as degenerate frequencies. If two normal frequencies are same, that is two different normal modes have the same frequency, then we call them as degenerate frequency. And modes will be degenerate normal modes. Okay, so remember this, modes will be called degenerate normal modes and frequency will be called degenerate frequencies, which means omega I will be equal to omega j. Just like here you will get same value for omega 1, omega 2, omega 3, omega 4, omega 5. So here omega 3 and omega 5 are same, so means these omega 3 and omega 5 are degenerate frequencies, and rest the omega 1, omega 2, omega 4 are non-degenerate. So that's how you find which frequency degenerate and which is non-degenerate. Now the lowest frequency, you have multiple values of frequency, so lowest frequencies in them will be called the fundamental frequency. The lowest normal frequency is called the fundamental frequency, and corresponding mode is called the fundamental normal mode. So when you get these values, then the lowest frequency in them will be called fundamental frequencies, and corresponding to that the mode you will find is called the fundamental mode. Now see, the next frequencies means you will get some frequency greater than the fundamental frequency, that is called the first overtone. Then greater than that frequency is called the second overtone. Means when you arrange them in the increasing order, then first is called the fundamental frequency or the fundamental normal mode, and the next frequencies are called the first overtone, second overtone, third overtone. The next higher values of frequency are called the first overtone, second overtone, and so on. So let me give you this thing. So the lowest frequency is called the fundamental frequency, that is FF, and the next frequency which is greater than this is called the first overtone, and second overtone, third overtone. So that's how you know what is the overtone. Now let's see the equation which we already discussed. Here this matrix represents the values of frequency. This will give us the normal frequencies. Now here we have normal modes, so there will be some particular equation, means this is just like a simple harmonic oscillator equation. So there you are having the x double dot and the x here, so that there was a solution in terms of x. So here will be some solution also. So here we will assume some solution. So that will be a wave definitely, because it's an oscillation thing. So if it is wave, then exponential I omega t will give you your oscillation terms, and these two constants will give you your means natural solution. Means here we have taken the Ci constant, which means if you have multiple modes, okay, means particular frequency you have particular mode, so n frequency will give you n modes. So if you want to find the superposition of some particular modes, then you will use the Ci constant, means C1 eta 1, C2 eta. इस तरीके से you can that's how you can find the superposition of modes and the particular mode corresponding to those modes. So that's why we have placed the Ci constant here, and this Ai is called the normalization constant, which make this equation a normal equation. Okay, so that's why we have taken these two constants here, and this exponential I omega t represent the oscillation of the wave. So that's how we assume this solution for this. Now let's see the equation and substitute this solution here. So what we can find here, so what is the useful result we can find, let's see. We know this equation. This equation is getting from here after multiplying with t ij inverse. So we have this equation, the original equation. Now substitute in place of eta I this one, means we have to substitute eta I double dot. So eta I double dot will give you exponential I omega t, then I omega will came out, then again second order derivative will give you I omega again. So it will be I omega square ci ai e exponential I omega I t and tij, and this will be as it is. Now in place of this I square will be minus, so minus omega I square tij, and this is again same eta I. So we have this. Now take the eta I common, it will be vi minus omega I square tij. Now see, this equation have the solution, means if eta equal to 0, then that will be called the trivial solution, because it's like you have x plus y plus z equal to something, means then you will place x equal to 0, y equal to 0, z equal to 0. If x plus y plus z equal to 0, or 3x plus 4y plus 3z equal to 0, and you place x equal to 0, y equal to 0, z equal to 0, so that is called the trivial solution. So we don't need that, because that is no use to us. So we won't place this eta equal to 0, we will place this equal to 0 to get the non-trivial solutions. So we will substitute this equal to 0, and this equation is called a secular equation. For non-trivial solution, this should be equal to 0. This is called a secular equation and may be used to find the normal frequencies. Now when you will place this equal to 0, this is some matrix, and determinant of this will give you your values of normal frequencies. So that's how you get your normal frequency. You will solve this equal to 0, and that's how you will get. Means you should have your potential energy matrix, you should have your kinetic energy matrix, then you can substitute them here and you can find the value of omega I, and that is your normal frequency. We will see some examples, just wait. And corresponding to every frequency you will have the corresponding normal mode, so that is represented by this x1. So Vij minus omega 1 square Tij corresponding to x1 equal to 0, where this x1 is a column vector, because here you will get 3 into 3 into 3 vector, and you will solve this, so this will be a column vector. So this solution will give you your omega. So let's see some things. Means what is this normal mode? We can represent it in the form of column vector, that is a1, a2, a3. So let's see, we will get some this kind of form. Means when you solve this equation, then you will get here a2 in terms of a1, a3 in terms of a1, so you will get some x1 just like this, 2a1 minus 3a1. Then you can take the a1 common, and this inside this thing, this can show you your normal mode. So that's how you can find how the particles are oscillating. So that is the meaning of normal mode. So now we need to normalize this equation. We know this equation from here. So how can we normalize? What is the meaning of normalization? So see, here you are somewhere you have matrix, somewhere you have something else. You need to make a simple equation which include only numbers. So how can you do that? So multiply with x1 here and x1 here, it is as it is. Now see, if you multiply with transpose of x1 transpose this side and x1 transpose this side. So if this is a column vector, so this will be a row vector. So 1 into 3 and 3 into 1, and this is 3 into 3. So it will give you 1 into 3, and 3 into 1 will give you, means 1 into 3, 3 into 1 will give you 1 into 1. So you can check this, that complete solution of this will give you a single number. This will dissolve to a single number, and this will dissolve to a single number. Then this equation will be normalized. And it is customary to take this value as 1 for the normalization condition. Okay. So you will, when you take this equal to 1, then this is nothing but equal to omega 1 square. So that's how, if you have your normal mode, and then you can find your corresponding normal frequency, just substituting values here, and you have Vij. Okay, so that's how you normalize, and that's it. So let's see some theory then we will see some question. So now see, these are your normal modes at normal frequencies, but you will have definitely some mixed mode. Okay, means there when particles are oscillating at different frequencies, so you get all those frequencies by the superposition of these normal frequencies or normal modes. There will be some modes which are not normalized, so you can get them, mixed mode will be there, so you can get them by using the superposition of these normalized modes. So this will be something like C1, X1, C2, X2, C3, X3, and that will give you your normalized, means any mixed mode can be written in that form. Like this. You have any mixed mode, so that can be represented in terms of these normalized modes, C1, X1, C2, X2, and these X1, X2, X3, all are orthogonal to each other and all are independent of each other, and they are linearly independent. So you know this equation, we have discussed it in many times. We have discussed this in quantum mechanics also, that how we place the every single mode differently, and we can write the superposition as your wave function. So all the mixed modes where particle are oscillating at different frequencies may be expressed as superposition of normalized mode. So what is the purpose here? To find the normalized mode and normalized frequencies, then we can find anything by using them. So they can be expressed as superposition of normalized modes. For this purpose, it is customary that x1, x2, x3 should be independent of each other there. And best practice to choose independent modes is that we choose orthogonal modes, because you can see that in the xyz axis plane, these x and y and z are both all are orthogonal to each other, and that's why the movement along the any one of them is independent to any another. Okay, so movement corresponding to x will be independent of y and independent of z. So that's why we take all these x1, x2, x3 as orthogonal. So modes is that we choose orthogonal modes because they are independent of each other. So I hope you understand this thing. So that was all the theory about the small oscillations which you need for the exam. So let's see some questions now. A particle of mass m is moving in a potential of the form. So potential is given, and what you need to do is you need to find a potential matrix, and so that you can find the oscillation frequencies. So you need to find the normal frequencies. So how you can find? So for a particle, so to get the normalized frequency, what you need? See from here, first you need to get this secular equation. In secular equation, you need to get Vij and Tij. So you need potential energy matrix and you need kinetic energy matrix. I already told you how to find them. Let's see by an example. So if potential energy is given in this form, then for a particle mass m, the kinetic energy will be in terms of x, y and z. So it will be half m x dot square y dot square plus z dot square for the particle. So you have kinetic energy and the potential energy. Let's see how we write the matrix. So you remember half should be as it is, and then you will see x dot here, y dot and z dot. X dot is 1, y dot is 2, z dot is 3. So x dot will be 1 1. So in place of 1 1 it will be corresponding coefficient, that will be m. Then 2 2 it will be m, and 3 3 it will be m. So that's how you find the kinetic energy matrix. Now see for the potential energy. You will place half as it is, and then you will see x as 1 1, y as 2 2, and z as 3 3. Means x is 1, y is 2, z is 3, and xy will be 1 2. So you can write 2xy as xy yx, because you need to write a symmetric matrix. So xy yx will give you 1 2 and 2 1, and corresponding to them coefficient will be m omega square. For x square it will be 3 m omega square. So it is 1 1 pe, in place of 1 1 you will get 3 m omega square. So 3 m omega square. In place of 2 2 you will get 3 m omega square. It is 3 m omega square. In place of 3 3 you will get 2 m omega square again. So it is same. Now in place of 1 2 you will get 2 m omega square. Not 2. It is x y and yx. So it will be 1 1 into m omega square. So 1 2 pe, in place of 1 2 1 2 it will be m omega square, and 2 1 means yx, it will be m omega square. So 2 1 it is m omega square, and rest are not given, so we will place 0 there. Now you have your potential energy matrix, you have your kinetic energy matrix. So what you need to do is you need to write a secular equation, that is Vij minus omega. This is the normalized frequency you need to find, and Tij. So we will just this minus omega naught square to this. So it will be m omega naught square, m omega naught square, m omega naught square, and subtract this from this. So it will give you 3 m omega square minus m omega naught square, and these terms you will get. Now this is a determinant you need to solve. So you will solve by this row because it will be simplified then. So take this outside, then this will be this multiply this minus this multiply this. So this will be, now you can use the formula a square minus b square. B is m omega square whole square. So it will be a plus b, a minus b. So that will give you this 2m omega square minus m omega naught square, 4m omega square minus m omega naught square, 2m omega square minus m omega naught square. Now place everyone equal to 0 and you will get your different normal frequencies. From here you will get omega naught as under 2 omega. From here you will get your omega naught as 2 omega. From here again you will get under 2 omega. So there where you have these three generalized coordinates. That's why you are getting 3 generalized or normal frequencies. So under 2 omega, 2 omega, under 2 omega. This is non-degenerate, and these two are degenerate frequencies. So I hope you understand how we find it this. We just find it the kinetic energy matrix, that potential energy matrix, then we substitute in this formula, just like you did in the eigenvalues. So just like the same, you need to do here, and you can find this values. Let's take one more example. Lagrangian for a 3-particle system is given by this. So Lagrangian is given, this is kinetic energy, this is potential energy, you can see. So where A is real, then one of the normal coordinates has a frequency omega given by. So we need to find the frequency corresponding to any one of the coordinate. So 4 options are given. So let's find omega, then we will see that which option is correct. So from here, eta 1 dot will give you 1 1 position, corresponding to coefficient will be 1. So 1. Here for eta 2 it will be 1 only, and for 3 also it will be 1 only. So you will get your kinetic energy matrix. Now for the potential energy, see this, there is no half here, so we will multiply with half and multiply with 2. So at 1 place you will get 2a square, at 2 place again you will get 2a square, at 3 place you will get 2a square, and you can write means then you will just multiply with 2 here, so it will be 2 here also. So you can write it as 3 1 and 1 3. So at 3 1 and 1 3 you will get minus a square. So 3 1 and 1 3, it will give you minus a square. Now you have potential energy matrix, you have kinetic energy matrix. Substitute in the secular equation, omega values will be, solve the determinant, it will give you omega equal to under root 2a, omega root 3 and a. So these will be C and A option will be correct here. It was a multiple selection question. So that's how you can find. Let's see one more question. Find the normalized frequencies for the oscillatory system such as shown figure. So here the particles have the same mass, 3 springs we have. This is a rigid wall. Now see, first we need to find the equation for the kinetic energy and potential energy, then we can find the matrix and hence the normalized frequencies. So first kinetic energy, we take these equilibrium positions, and this displacement represented by x1, this displacement represented by x2 by this m. So displacement dot will give you your velocity corresponding to them. So kinetic energy is simply half m, x1 dot square, x2 dot square. Now see, potential energy is nothing but kx square by 2, and this where x is displacement of the spring. So for this first spring, displacement will be x1 outward. So potential energy for the first one is kx1 square divided by 2. For this third one, this displacement is in this direction, and this will means compressed. So potential energy for this will be kx2 square by 2. Now see for this this third one, here this spring length is decreasing, and here this spring length is increasing for this one. So net increase or decrease will be x2 minus x1 for this spring. So you will write x2 minus x1 square k divided by 2. So this will be your potential energy, this is your kinetic energy. From here you can see this will be 2 generalized coordinate you have. So there will be 2 into 2 matrix. So corresponding to this coefficient will be m, and 2 corresponding coefficient will be m. Same for potential energy, you can see. Take the half common, it will be kx1 square, kx2 square plus, open this square, kx2 square plus kx1 square, and minus 2 kx minus 2 kx2 x1, and there you can write that 2x2 x1 as x1 x2 and x2 x1. So then you will find your values. It will be kx2 square, kx1 square, kx2 square. It will give you 2 kx1 square, 2 kx2 square. So it will be 2k coefficient here, 2k coefficient here. You can see this, you can find this v, just we did in the last questions. So corresponding potential energy matrix will be this. Now you know how to solve. It is v minus omega naught square t, that is your secular equation. Solve for omega, solve the determinant, you will get these two values as your normalized frequency, under root k by m, under root 3k by m. Let's see last question for today. After solving some more questions, you will be able to solve any kind of question corresponding to small oscillations. So find the normalized frequency for the system solved. Now again, let's assume the equilibrium position. So it will be displacement will be x1 for this, x2 for this, x3 for this. So kinetic energy will be half m x1 dot square, x2 dot square plus x3 dot square. Now we need to find the potential energy also. So see, we will take separately individual springs. So first take this spring. For this spring, this x1 is decreasing. First fix this point. So this x1 is decreasing this length, and this x2 is increasing this length. So net change in this spring will be x2 minus x1. So for this spring, potential energy will be k x2 minus x1 square divided by 2. For this second spring, fix this point, then this x3 is increasing this length, and then fix this point, this x2 is decreasing this length. So net increase or decrease will be x3 minus x2 k divided by 2. Same for this third spring. This x1 is increasing this length, x3 decreasing this length. So net increase or decrease will be x1 minus x3. So x1 minus x3 divided by 2. Now open this square and you will get 3 into 3 matrix. Same here, you will get 1 1 place. Coefficient will be m, coefficient m, coefficient m. So kinetic energy matrix will be this. Potential energy matrix will be, you can find x2 square plus x1 square plus minus 2x2 x1, then x3 square plus x2 square. So add these terms. So whatever corresponding coefficient you will get for the x1, x1 square will give you for the 1 1 position, x2 square will give you for the 2 2 position, x3 square will give you for the 3 3 position, then x1 x3 x3 x1 x2 x3 x2 x3 x2 x1 x1 x2. You will get your all the coordinates. You will find the potential energy matrix and solve for this again using the secular equation, that is v minus omega square t. Solve the determinant, you will get omega as 0 and under root 3k by m and root 3k by m. So these are the degenerate values and this is non-degenerate value for the normalized frequency. So that's it for today. In the next lecture we will see about how to find normal modes also. Okay, so we'll meet you in the next lecture. Thank you everyone.